Assalamu alaikum students. The topic of our today's lecture is field effect transistors. Now this is another type of transistors apart from the ones that we have already studied, that is the BJTs. Let's compare the two transistor types, the FETs and the BJTs. The similarities are that both of these can be used for amplifiers, for development or the design of amplifiers, for the design of switching devices, and for implementation of impedance matching circuits. The difference between these two are basically that you have already seen the equivalent circuit of a BJT. It was a current source which was controlled by another current. It was a current source controlled by the base current, while the FETs are voltage controlled current sources, and the voltage that controls this source is basically VGS, or the voltage between the gate and the source. And we will see what is the gate, what is the source, and what is the drain, which are the three terminals of a BJT of an FET, sorry, as compared to a BJT which has three terminals, which are the emitter, collector, and the base. FETs are less sensitive to temperature variations and are more easily integrated on ICs. So they are used mostly in situations where there is a wide range of temperature affecting the electronic circuitry. Another important point is that the FETs have a higher input impedance as compared to the BJTs, which have very high gains. Now, the JFETs have two major types. The FETs have two major types, the JFETs and the MOSFETs. JFETs are basically the junction FETs, and MOSFETs are metal oxide semiconductor FETs. And there are two further types of MOSFETs, the D MOSFET or the depletion MOSFET, and the E MOSFET or the enhancement MOSFET. Now the JFET construction is as follows. We have an N-type material, and on two ends of that material we put ohmic contacts, or the metallic contacts, which are which make a drain and a source terminal. And we have P-type material on two sides of that N material, and both of these materials are connected through ohmic contacts and connected together, and they form a gate. So we have got three terminals in an FET, and what are those three terminals? The drain, the source, and the gate. And we have an analogy of a water valve when we see the operation of a JFET. As much we open the gate, the water flows accordingly. If we open the gate more water would flow out. Similar is the case in JFETs, that if we increase the voltage VGS, the current ID, or the current from the drain, increases. Now let's have an example in which we connect the gate to the source, which means that the voltage between the gate and the source is 0, and we increase the voltage between the drain and the source. as we go on increasing this voltage, the current through this current from the drain to the source, it increases, but along with it, as we go on increasing the drain to source voltage, the depletion regions between the P and N type materials on both the sides go on increasing, and a point comes when both of these depletion regions combine, or and that point is called the pinch off, and the voltage at which such a situation occurs is called the voltage pinch off voltage. Now this is a special case in which we have put VGS equal to 0, and as we go on increasing the voltage between the drain and the source, as you can see, we have a variable voltage source between the drain and the source. As we go on increasing it, the current through it increases, and a point comes up at which the depletion region on both of these ends keep on increasing, and a point comes when both of these depletion regions uh, are connected to each other, so thus blocking the path of further current. But what actually happens is like this, that as we go on increasing the voltage between the drain and the source, or the VDS, a point comes on the VDS axis, which means that a point comes when the current would no longer increase as it was increasing in the earlier range, and it would saturate at a certain level. That particular saturation level of current is called IDSS, and that is a very important characteristic of a JFET. And the other important characteristic of the JFET is VP, or the pinch off voltage, right? But what pinch off voltage we would be using in JFETs would come in further slides. This particular situation in which we have put VGS equal to 0, and ID comes out to be IDSS after VP, that gives us the only important characteristic of IDSS. Let's see how do we get the value of VP. Here also the uh, the phenomena of the pinch off is explained, in which the VDS has increased up to a value equal to or more than VP. At that particular point, the ID value saturates to IDSS. Now, and now we see a situation in which we have a negative voltage between the gate and the source. As you can see in the diagram, we have put a battery in the reverse direction, and the value of that battery is 1 volts. So what would happen in this case? As we go on increasing the value of the voltage between the drain and the source, the the current would increase, but since we have put a negative voltage potential between the gate and the source, it the current ID uh, would saturate at a lower level as compared to IDSS. If we further increase the value of the negative potential between the gate and the source, the saturation current would reduce further, and a time would come when ID would remain at 0, whatever the value of the voltage between the drain and source is. That particular value of VGS at which the current ID cannot lift itself from 0, that particular uh, voltage between the gate and the source is called the pinch off voltage, or VP. That is the second important characteristic of a JFET, right? So these are the two basic characteristics of a JFET: IDSS and VP. Let me remind you that IDSS is the saturation current when VGS is kept at 0, and VP is the voltage between the gate and the source when such that the current ID does not increase from 0, whatever the value of VDS is. So these are the two important characteristics of a JFET. Now let's see the you can see that as we increase the negative potential between the gate and the source, for example, we put it at -1 volts, we get an IDSS ID saturation at 4.5 milliamperes. When we increase this negative voltage between the gate and the source to -2 volts, the current ID saturates at 2 milliamperes. When we increase the VGS up to -3 volts, the current ID saturates at 0.5 milliamperes. And if we further increase the negative voltage between the gate and the source to -4 volts, the current remains at 0, and it does not pick up from at any point, whatever the value of VDS is. We keep on increasing the value of VDS, but the current remains at 0. That particular value of VGS is called VP, or the pinch off voltage. Here in this case, the pinch off voltage is -4 volts and the IDSS is 8 milliamperes. The region to the left of the pinch off point is called the ohmic region, because in this case, as we increase the voltage between the drain and the source, the current increases. But after this particular value of VP, the current remains saturated at that particular point. Now, the JFET can be used as a variable resistor also, where VGS controls the drain source resistance RD. As VGS becomes more negative, the resistance RD increases, right? RD is equal to R naught over 1 minus VGS over VP whole square, where R naught is the resistance with VGS is equal to 0, and RD is the resistance at a particular value of VGS. If we have a p-channel JFET, what would happen is that it would behave just like an n-channel JFET, except that the voltages and the currents, voltage polarities would be reversed and the current directions would be reversed. And one more thing, as we go on increasing the voltage between the drain and the source, depending upon which VGS is chosen, it would follow a breakdown region, and the breakdown region would come at a certain value of VDS. As we increase the the value of VGS, the breakdown voltage or the breakdown voltage VDS comes earlier. For example, for VGS equal to 4 volts, it comes at about minus 20 uh, volts of VDS, right? And what happens is that the value of the current ID increases uncontrollably, and this would happen only when VDS becomes more than VDS maximum. This VDS maximum is controlled also by VGS, and if we increase the value of VGS, this breakdown point or VDS value comes earlier, as you can see in the above diagram. And actually what phenomena is happening over here is that as VGS is increasing to a more positive value from 0 to 1 and 1 to 2, 2 to 3, 3 to 4 and 4 to 5, what happens is that the depletion zone increases and ID decreases. Eventually ID becomes 0 amperes, but as we go on increasing the value of VDS, the breakdown region comes in, sets in, and it starts an uncontrollable ID. Here are the symbols of both types of JFETs. The N-channel JFET, in which the gate terminal points towards the device, while in the P-channel symbol, the gate channel points out of the device. Now we have got three examples, in which the first one is the one in which gate and source are connected, which means that VGS is equal to 0, and as we go on increasing VDS, the voltage between the drain and the source, the current increases and it saturates at a value of IDSS. In the B case, what happens is that we have put a negative voltage between the gate and the source, and it increases to a value and it is so much that whatever the value of the voltage between the drain and the source, ID would remain at 0. Third case, or the C case, is the one in which the value of the voltage between the gate and the source is smaller than the pinch off voltage, and what happens that a certain value of ID is maintained. As we go on increasing the voltage between the drain and the source, it would increase, and the ID would saturate at a certain point. Depending upon the higher and higher values of VGS, the saturation of the saturation current becomes smaller and smaller. As in BJTs, beta indicates the relationship between IB input current and the output current IC, or the collector current. In the JFETs, the relationship of VGS input and ID output is a little more complicated, which is given by Shockleys. Actually, these JFETs were developed by William Bradford Shockley, and the equation that relates the two variables, that is ID and VGS, is ID is equal to IDSS into 1 minus VGS or VP whole square. Here the two variables are VGS and ID. This particular equation was developed by Shockley. Here you can see we have an IDSS value and a VP value also. IDSS and VP are the characteristics of that particular FET, while ID depends on VGS and VGS depends on IG. Let's see how do they depend upon each other. For example, as we go on increasing the value of VGS, if it is at 0, the curve would saturate at IDSS. As we increase the negative negative potential of VGS, as you can see on the left hand side, minus 1 volts, it would the current would saturate at 4.5 milliamperes, as you can see in the diagram. As we further increase the value of the negative potential between VG and between G and S, or the gate and the source, up to minus 2 volts, what happens is that the current through the through the drain ID saturates at 2 milliamperes. Similarly, if we increase this to minus 3 volts, then the VGS would then ID would saturate at 0.5 volts. If we further increase the voltage between the gate and the source to minus 4 volts, what happens is that the current through the drain does not increase from 0, and it remains at 0, as you can see a blue line on the x-axis of VDS. Now, how do we plot on the JFET transfer curve? We have, as I have already told you, we have got two characteristic values of a particular JFETs, and those two characteristic values are ID and VP. And we can find these values in the specification sheet of a particular FET. In the first step, we write the Shockley's equation, which is ID is equal to IDSS into 1 minus VGS over VP. First of all, we put VGS equal to 0. In that case, ID comes out to be IDSS. So we can plot a point at VGS is equal to 0. We can plot ID equal to IDSS. In the second step, we have ID is equal to IDSS into 1 minus VGS over VP whole square, and we put the value of VGS equal to VP, or the pinch off voltage. In that case, ID would be equal to 0, because in this case current is cannot increase from 0, whatever the value of the voltage between the drain and the source is. In step number 3, solving for VGS equal to 0 volts to VP, ID is equal to IDSS into 1 minus VGS over VP whole square. And in this case, we have put a certain value of VGS, for example, minus 1 volts. If we put that value, then the value of ID comes out to be 4.5 milliamperes. And conversely, for a given value of ID, VGS can be obtained from the same Shockley's equation. You can try some mathematics and convert this Shockley's equation of ID is equal to IDSS into 1 minus VGS over VP whole square, and try to find out the value of VGS. VGS would come out to be VP into 1 minus under root ID over IDSS. Here in this case, you can see the curve that we can draw by putting different values. First of all, we can put the value of VGS equal to 0. In that case, the value of ID comes out to be IDSS. If we put the value of VGS equal to VP, or minus 6 volts, the current value would be 0. So in case of VP equal to VGS being equal to VP, or which is minus 6 volts in this case, the current would be 0. That's why this point is plotted at the x-axis at minus 6 value of volts value of VGS. While at VGS is equal to 0, ID comes out to be IDSS, which is 12 milliamperes in this case. Now we try to find out the value of VGS when ID is half of IDSS, or half of 12, which is 6. Uh, if we put this value of IDSS in this equation, for example, VGS is equal to VP into 1 minus under root ID over IDSS, we come up to a value of minus 1.8. Now, in case we put a value of 3 volts, 3 3 minus 3 milliamperes in place of VGS, we get a value of ID equal to 3 also. So again, we can plot another point. So now we have got 4 different points. We can join these points to form a curve. This is a characteristic curve, or the transfer curve of a particular IDSS, of a particular FET, sorry.